Hello and welcome to Chandler Science AP Physics 1 Dynamics Pulleys. In today's lesson, we're going to talk about pulleys, believe it or not. We're at that point, ladies and gentlemen, where we have covered the concepts. We know Newton's laws. We know how to make free body diagrams. We know all that stuff, and we have to start putting all that stuff to use. There's really nothing else to do conceptually. All there is to do left now is practice, practice, practice. So we're going to practice with some pulleys. Today we're going to do two problems. It's going to take us about 20 minutes. So let's dive right in. Don't forget, if you are in my class, you are taking notes. You are following along in your notes, and you're going to post one question on the discussion forums and then reply or answer someone else's question on the discussion forums. If you are from somewhere else on the internet, welcome and hope you enjoy. Let's go ahead and dive right in now and do some problems with pulleys. All right, so here we have a fairly straightforward and simple pulley problem. It's a very typical problem you'll see on AP exams or on the questions. We have two masses hanging from a pulley on either side of the pulley. And typically you'll see language like an ideal pulley or a massless pulley. They're just letting you know that you don't have to worry about any of the friction or any kind of like rubbing of the rope with the pulley itself. So we call it an ideal pulley or a massless pulley. So typically questions like this, they're going to ask you to find the acceleration of the blocks, and then they're going to ask you to find the tension in the rope. That's the most common thing they're going to ask you to find. So let's practice that. The first thing we want to find always is acceleration. You always want to find acceleration first, and then after that we can find the tension in the rope. So first acceleration and then tension. In order to find the acceleration of the blocks, we have to recognize that these blocks are connected by the rope, and they're both going to accelerate in the same way because they're both connected by a rope, right? So if M1 accelerates down, M2 will accelerate at the same rate, but just up, because that's how pulleys work, right? So we have to recognize that M1 and M2 are going to be treated like they're the same object. So they are the system. In this case, our system is going to include M1, M2, and the rope, because it's also going to be accelerating at the same rate, right? They're all accelerating together. And if they're all accelerating together, we can treat them like they're one big object, right? And coincidentally, the rope has no mass in this case also. So we treat it like it's a special magic rope, right? All right, so what is the implications of this? Well, the implication is that the tension force, if the system is both masses plus the rope, the tension force is internal to the system. And if you remember Newton's first law, an object in motion stays in motion, an object at rest stays at rest, unless acted upon by an external net force. Well, if the rope is internal to the system, it's not going to do anything to change the motion of the system. It cannot accelerate the system because it's internal to the system. So let's draw a free body diagram for our blocks. That's always step one. M1, we have weight down, M1G, and then up we have that tension force. And then for the second, this is M1, and then for the second object, M2G, and then up where we have that same, a little better. Oh my gosh, I just have a hard time drawing arrows. There we go. Tension force. Now, the upward tension force is the same, right? It's the same rope, so it's the same tension force. So are there any external forces acting on the masses and are on our system? And there are, right? It's the weights. The weight force down here and this weight force down here, those two weight forces are both external to the system because they're being caused by the Earth, which is not part of our system. Our system is just the two masses and the rope. So that's an external force. That can cause an acceleration on our system, but not the tension force because it's internal. So we're going to set up our net force equations. And before we do that, though, let's take a look at the pulley and direction. Direction has always been very important to us. We've always called to the right positive or up positive, and we've always called left or down to be negative, but that's going to be a little different here with pulleys. Pulleys kind of change the game when it comes to, they change the rules when it comes to direction, because if you'll notice, both of these weights on our masses are down, right? They're both down. So you might think, oh, well, they're both going to be negative, but that's actually not the case. We're actually going to call things that go around the pulley clockwise to be negative, and things that go around the pulley counterclockwise to be positive. That's the conventional way. If you want to switch them, you can, but this is the conventional way of thinking about it. So let's look at the weight force of M1. The weight force on M1, if you think about, if you kind of like trace it back up the pulley, right? We know the weight force here on M1 is going down this way, right? Down like that, okay. Well, if you kind of trace it back up, it's going down the rope this way, down the rope this way. If you kind of trace it back, you see how it's kind of going around in a counterclockwise fashion around the pulley? So we're going to call this one positive. Now look at the same way for M2. M2 has its weight down this way, but trace it back up. So it's going down, but look what happens when you go back up. See how it's going down the pulley that way? That means it's going around the pulley clockwise. Think of as the pulley as your clock face, right? We have 12 o'clock, 6 o'clock, 3 o'clock, 9 o'clock. And if you kind of trace the arrow back up, kind of backtrack the arrow for the weight force arrow of M2 back up to the pulley, you see how it's going in a clockwise fashion. So that's actually going to be negative. So M1G's weight force is positive, M2G's weight force is negative. So what is our net force equation? And the only forces acting on this object that are external to our system are the weight forces. So we have M1G minus M2G, right? Because we said it's negative because of the way the pulley changes the directions. So what do we got? Well, we know these masses are these objects. M1 was 12, so G is 10, so we got 120. Minus M2 is 4 kilograms, so M2G is 40. So our net force then is going to be 80 newtons. Now we're going to do Newton's second law to find the acceleration. Now we know the net force is 80 newtons divided by the mass of the system. So it's not just one mass or the second mass, it's the mass of everything, which in this case is 16 kilograms. So the acceleration of this system will be 80 divided by 16, which is 5. Acceleration is 5 meters per second squared, right? And for M2, it'll be accelerating. Acceleration is positive, right? So both objects are accelerating in the positive direction. They're both M2 will be accelerating up this way. If you think about it, if you keep the arrow going up, right? That's going counterclockwise around the clock face, around our pulley, so it's positive. And M2 is going to be going down this way. M1 will be going down this way around the clock face, and also in a positive direction. So they're both going in positive directions. Okay, now what about the tension in the rope? The tension in the rope, we're going to do Newton's net force equation here. Now we know. Newton's second law. I said that right the first time. Newton's second law for what we're going to do though. Sorry guys. What we're going to do is we're going to pick one of the objects. We're now going to say our system, let's say, is M1. We're going to change it from the system being both blocks plus a rope. Now we're going to say now our system is just one of the blocks. So let's pick M2, right? It doesn't matter which one you pick, or M1. I mean, let's just pick M1. It doesn't matter which block you pick. So let's pick one of them. We'll just pick M1. All right. So we know the acceleration on. We're going to use the equation F equals ma. We know the acceleration on M1 now is 5, which is found it, and we know the mass on M1 is 12. So we're going to say, okay, the mass 12 times acceleration, which is 5. And so the net force we know on that block is going to be 60 then. Because 12 times 5 is 60. And now we're going to kind of unpack the net force, right? Well, what are the net forces on just M1 block? Well, they're the weight down and the tension force up, right? Let's go back to the free body diagram for M1. We have the weight M1 down, M1G minus tension force, right? Because remember, it's up. The tension force is up this way, which if we trace it back around the pulley is the negative direction. So it's minus tension. We know that must equal 60 newtons. So now we're just going to solve for tension. So I know M1G is 120. I'm going to subtract the 60 over to this side, and I'm going to add the tension to the other side. So I'm going to get 120 minus 60, and then positive tension. So I'm going to get 60 equals T. So my tension force is 60 newtons. So I know T here equals 60 newtons for both of my on both free body diagrams, right? Because the tension force, it's one rope, so same tension in both situations. One of the tricks I tell my students that you can do to kind of check to see if your answer makes sense, your tension force should always be less than the larger object's weight, but more than the smaller object's weight. So we know that M1's weight force is 120, and we know that M2's weight force was 40. So we know that the tension force should be in between there somewhere, right? And it is. It's 60, and this makes sense because if the larger weight M1 pulling down on this on the rope, we know it's going to accelerate down. So the net force should be down. So the weight should be greater than tension up, and it is. And for M2, we know it's going to be accelerating up. So the net force should be up. So the tension force up should be larger than its weight down. So, and it is in this case because it's only 40 for M2. All right, so there we go. We found the tension. Oh, sorry, I didn't realize this was kind of cut off on the screen there, but we found the tension at 60. 120 minus 60, so tension here is 60 newtons. There you go. And we found the acceleration of the system in each block. All right, cool. Let's do another problem on the next slide. All right, everyone, here's another fairly typical problem you'll see on AP exams and on quizzes and tests. This time we have one of the masses is just hanging vertically, but the other mass, M2 here, is on an inclined plane. Sometimes it'll tell you there's a frictionless plane, other times it'll tell you that there is friction. We're going to do it with both, just because it's more fun, of course. So let's see. First, let's do it with when there's no friction. If there is no friction on the system, on the plane rather, then what is the acceleration of the blocks? And then what is the tension in the rope? So it's the exact same kind of process that we did on the previous problem. We're going to find the acceleration first, always, because we can find the acceleration on the system as a whole, and then we'll find the tension second, because once we have the acceleration, we can kind of look at one of the objects, kind of zoom in on that object and treat just the one object as the system, and then we can find the external tension force on that system. So let's go and set up our net force equations. And again, remember the pulley here, around this way is going to be considered clockwise, so it's negative, and then around this way, counterclockwise will be positive. So be very, very careful now on problems like this with your directions. Okay. All right, so let's see. We got net forces here. Actually, you know what? I got ahead of myself. We should draw a free body diagram first for each object. So let's do M1 first. We have M1 straight down, M1G. Upward, we have tension. On M2, we have its M2G down, and then we have the tension force up this way, and we gotta have normal force. If I could draw always like my biggest hurdle in life, drawing straight lines. Whoa, what's that? A normal force up that way. Okay, that should be pretty much it. We're gonna have components of the weight force. Let's go ahead and just draw them on here while we're thinking about it. So let's do red for parallels to the block, so down the ramp, sliding down the ramp in red, and we'll do blue for drilling into the ramp, right? So down the ramp and then into the ramp. And of course we know that this angle here will be 30 degrees. All right, now you have all that kind of set up. Let's look at what our net force equations, our net force equation is going to look like. Back to black, please. Come on. There we go. Did I do it? There we go. Okay. All right, net force. Let's say net forces here are going to be on the system as a whole, right? So what is the only forces that are causing our system to accelerate? Remember, our system here is going to be pretty much everything, right? Both masses, M1 and M2, and the rope, okay? So tension force is internal. It's not going to do anything. The normal force is actually external, but it's being canceled by this component of the weight force. So the normal force, while it is external, is not going to be doing anything to our system because it's being canceled by this component of the weight force of M2. Whoa, goodness. Sorry about that. All right, so as before, the only forces that are causing our system to accelerate are the weight forces. So it's going to be M1G. Actually, no, it should be negative, right? Because it's going. So let's do negative M1G plus M2G. But it's not M2G, is it? It's going to be this component of M2G because that's the one that's actually going down the ramp. The other one, this component here of M2G is being canceled out by the normal force, right? It's not actually causing our block to accelerate. It's going into the ramp. We want the one that's pulling us down the ramp. So we're going to look at M2 sine theta. Did it again, sorry guys. M2G sine theta, okay? So let's see what are all our forces here. And that should be it, right? Again, we're going to do frictionless first, and we'll add friction in a second. All right, so M1 is 8, so we have negative 80 newtons there, plus, so M2 is 30, M2G is 30, times sine of 30 also, so it's going to be 15. So it looks like our net force on this system is going to be negative 65 newtons. Negative just because it's going around the pulley in a clockwise fashion down this way, right? So now we have our net forces. We're going to say, okay, what's the acceleration of the system? Newton's second law. Acceleration is the net force of the system over the mass of the system. So acceleration will be the net force, negative 65 newtons, over the mass of my system, which is 11 kilograms. So the acceleration of my system is going to be a negative, and I'm not good at math in my head, so I'm going to punch it in my calculator. 65 over 11. And that's going to be 5.9. Let's just call it 6. So negative 6 meters per second squared. I'm not picky about decimal places and all that stuff, so negative 6 is fine. All right, cool. Now let's look at tension. All right, now define tension. So check mark on that. Okay, tension force. Okay, here's the rule, guys. I said before in the last slide, it doesn't really matter which mass you pick when you're trying to find the tension, right? That's true if they're both just hanging vertically. But I will give you a rule to follow. The rule to follow is once you've found the acceleration and you're trying to find the acceleration of, once you've found acceleration and you're trying to find the tension in one of the strings, you want to pick the object to focus in on. Make the system your object that has fewer forces acting on it, right? Typically the one that's just hanging there. M1 is easier because it only has weight and tension, right? M2 has weight, tension, and the normal force. Plus it's kind of at an angle, right? That makes it more complicated. So let's make the mass of M1 our system to find tension because it's easier because it has less forces acting on it. All right, so we know the acceleration of the system is negative 6, so we're going to have our net forces are going to equal our mass times our acceleration. We know that our mass for M1 was 8. Our acceleration was negative 6. Our net forces, let's kind of unpack what forces do we have acting on M1? Well, we have the tension and weight. So we have our weight down, negative 80, plus our tension force up equals negative, what's that, 48, right? 8 times 6. I have to do it, even though I know it's 48, I still punch it in. Negative 48. All right, so let's go ahead and just kind of add 80 to this side. So add 80 both sides. And we're going to get tension force equals 32 newtons. All right. And again, does that make sense? It should be less than the weight of M1 because it's going to be net forces down, this way. But it should be more than that red component of M2. And that red component of M2 was 15. So, yep, we're good. It's less than 80, but more than 15, so kind of it makes sense. So there we go. Tension of the rope is 32. And then the acceleration system was negative 6 because it's going around the pulley this way, right? Okay, cool. All right, so now let's solve the problem with friction. So we just did it without friction. Now let's imagine, okay, what if there was friction on this plane in between M2, the block M2, and the surface of the ramp? Okay, so let's say let's make up a coefficient, right? Let's say the coefficient of friction, turn my pen around. Let's say the coefficient of friction is, how about 0.35? Sure, why not? Doesn't really matter. Okay, if that's our coefficient of kinetic friction, then how does the problem change? Well, friction force is also an external force, right? Friction force, this block is going to be going up the ramp, right? That means that friction force is going to be pulling us down the ramp this way. Right? So friction force will be down the ramp because the tension force is going to be pulling us up the ramp. Okay, so that means that tension force is going to be in the same direction as that red component there. So let's go to red here again real quick and draw in our red friction force, right? So we have to include that now in our net force equations. All right, so what is the friction force? Well, remember that friction force equation for kinetic friction is equal to the mu times the normal force. Let's go and calculate that real quick. Mu is 0.35. Our normal force here is going to be the same as that blue component, right? because those are the two forces that are going, perpendicular to the ramp. So mg2 is 40, right? What is it? 30. So mg2 is 30 times cosine. Let me get my phone here to go scientific mode. So we got 30 times a cosine of 30, sorry. And I'm getting 25.9, let's call it 26. So that blue component there is 26, which means since there are no other forces acting on the block perpendicular to the ramp, the normal force is also going to be 26 newtons. So let's see, 0.35 times 26 newtons. And our force of kinetic friction will be 0.35 times that. And I'm getting about 9.1, so let's just call it 9 newtons. Okay, so friction force is also going to pull us down the ramp with 9 newtons of force. All right, so what's going to change up? So let's do this little in this section over here. I'm going to leave the rest of my work up so you can look at it. Let's do the friction problem in this little window. All right, so the force down the ramp is still going to be the same, right? 80, because it has no friction on M1. But M2 is going to have some friction on it. Let's go back to our net force equation. We have negative 80, because that's the weight of M1. And then we're going to have plus 15, because that's the weight force down the ramp. But we're also going to have plus a 9, because the friction force is also going to be pulling us down the ramp, kind of with gravity, kind of weird, but they're both going that direction because friction always opposes motion, and we know that M2 is going to be moving up the block, or up the ramp, right? So we get our net force. We should have a little bit less acceleration here, right, since friction is going to be fighting our motion. So this time our total net force, is going to be 15 plus 9 minus 80, and we're getting negative 56. So we have, which makes sense, 9 less force than before, right? So then our acceleration then for this system will be the net force, negative 56, over the total mass of the system, which is still 11. So 56 divided by 11, which is 5.1. Let's just call it 5, negative 5 meters per second squared. So we lost, what was it before? It was 6, right? So we lost about 1 meter per second squared, right? Because of the friction slowing us down. All right. And then we're going to say, all right, what about the tension in the rope? Let's see, will that change? It should change a little bit, right? The rope's got to pull a different force now that the friction is fighting us. So we're still going to look at mass 1, especially now that the friction, because again, now M2 has 4 forces acting on it, right? M2 has tension and weight and normal force and friction. A nightmare. Let's pick M1. M1 only has 2 forces acting on it. M2 only has, or M1, only has 2 forces acting on it. It's got weight and tension up. So much easier to look at M1. All right, so we know the acceleration on M1 is 5. So you have, its mass is 8. So 8 times negative 5. So we know the net forces are negative 40 newtons. So let's see, what unpack this symbol, right? It means all the forces in that direction. So we have weight down, which is negative 80, plus a tension force equals negative 40. So we're just going to add 80 over here. So the tension force is going to be 40. Oh, I'm writing over my face. Sorry, guys. So we know that tension is going to add 80 to both sides, right? Plus 80. Plus 80. So our tension force will be 40 newtons. And again, it makes sense. It's less than the weight of M1, but it is more than the sum of the forces down the ramp, right, on M2. So it's kind of in between, right, which makes sense. So it's going to, M1 is going to go down, but M2 will go up the ramp. And there we have solved that problem with both with and without friction. So cool. All right, guys. Hope that was helpful and kind of getting you started on solving some of the pulley problems on your homework packets and any other practice you're doing. Remember, guys, the only way to get better at doing these problems is to practice. That's why you have homework packets. You have to take the initiative and do problems from the book if you want. You have access to the Mastering Physics in the textbook. You can also, of course, just make up your own problem, right? Just draw a sketch like this at a different angle with different masses hanging. Maybe you have multiple masses hanging, whatever you want to do, but make it up. make up numbers for the masses and make up numbers for the ankle, and then solve it and show me in class, and I'll be happy to go over it with you and see if it's correct or not. All right, guys, that's going to be it for this video. In the next video coming up, I'm going to publish it right after this one. We'll look at just kind of tension in general without pulley systems. All right, guys, so as usual, don't forget, I have no life. You are my life, so questions are on your mind, email anytime, day or night. Don't hesitate to ask me, and I'll see you next time. Bye-bye.